right, so we have finished Module 1, and the last part of Module 1, which was Chapter 2, we talked about different operations we can perform on vectors, and I wanted to go through an example here that will remind us of all those different ways we can deal with vectors, and including different ways that we can represent those vectors. So if we take a look at this example here, we've got three different forces, F1, F2, and F3. Those are the red arrows. And for each force vector, we're given different information about it. So for F1, we're given that we have this angle of 45 degrees that F1 is making to this blue line. Now, what's the blue line? It is the projection of F1 onto the XY plane. So if I have my flashlight down here and I'm shining a light onto F1, the shadow that it makes is this blue line, the shadow it makes on the XY plane. So, okay, we've got our angle of 45 degrees, and then we've got another 30-degree angle, and that's the angle that this blue line is making with the y-axis here. Next, we have F2, and for F2, we're given these three different angles. That's the angle that F2 is making with each one of our coordinate axes, x, y, and z. And then finally, we have F3, which is a little small here, but it is 20 pounds, and it is pointing in this direction that is given to us by these distances from the XY axes and the XY plane. So we're going to walk through how to represent each one of these forces as Cartesian coordinate vectors. And so let's get into it. Let's start with F1. So for F1, the first thing to recognize here is that these are spherical coordinates. So if I recognize that these are spherical coordinates by recognizing that we're given this altitude angle, and the altitude angle is this 45 degrees, and we're given an azimuthal angle, which is this 30 degrees, right? So the angle that F is making with the XY plane and with an axis in the XY plane. So if I recognize that, then I can write my equations for the spherical coordinates of vector F, and those equations are Fx equals F times the sine of phi times the cosine theta. Fy is equal to F times the sine of phi times the sine of theta, and Fz is equal to F times the cosine of phi. And these equations are in your equation sheet that you will get with your exam when we take it, so no need to memorize it. The only thing you have to know is how to use it. So we have to figure out what the heck is F, what is phi, and what is theta. Well, F, I think, is fairly straightforward. We are given that the magnitude of our force vector F1 is 50 pounds, so that's our F. So F1 is 50 pounds. Now we need to know phi and theta. So in your equation sheet, it does say that phi is our altitude angle and theta is our azimuthal angle. So phi being our altitude angle. Now, the thing you have to remember with the altitude angle is that we are measuring from the positive z-axis. So my angle phi is first down 90 degrees from the positive z-axis down to the xy plane, and then we go down another 45 degrees. And so what that means is that our phi is equal to 135 degrees. right? Just 90 plus 45. Next, we need theta, which again is called our azimuthal angle. And theta is measured from the positive x-axis. And if we look at the direction, so first of all, we're given this 30-degree angle, which is not measured from the x-axis. Okay, so we're going to have to do a little transformation here. We are measuring angle theta from the positive x-axis, and this direction towards the positive y-axis would be positive. Okay, but we're going negative, so if we go negative 90 degrees, then we'd reach this negative y-axis, and then we add back 30 degrees. Now we're at our blue line. So I need to go minus 90 plus 30, so that is negative 60 degrees. Okay, and now we just need to plug all these numbers in to our equations up here, and we can solve for what each one of these components is. So F1x is going to be equal to 50 pounds times the sine of 135 degrees times the cosine of negative 60 degrees. F1y is equal to 50 pounds times the sine of 135 degrees times the sine of negative 60 degrees. And F1z is equal to 50 pounds times the cosine of 135 degrees. Okay, so get out my calculator, do this really fast. 50 sine 135 cosine negative 60 gives me 17.7. We're still in pounds. Okay, and then if I do 50 sine 135 times the sine negative 60, that gives me negative 30.6 pounds. And finally, for the z component, we got 50 times the cosine of 135 gives me negative 35.4 pounds. Okay, so let's check it first and make sure that this makes sense. So I got a positive number for x, and that makes sense. Our f vector f1, we're pointing along the positive x-axis. I got a negative number for y, and yeah, again, that makes sense. We're pointing down the negative y-axis. And for z, we got a negative component, and again, yes, that makes sense. We're pointing down the negative z-axis. Okay, so even if you didn't remember that we needed to measure from the positive x-axis at first, you would more than likely end up with a number here that doesn't make sense, and then that would be a good reminder to go revisit and make sure that you're measuring from the positive x-axis or the positive z-axis. Okay, so now we have our x, y, z components. The last step for F1 is to just write it in our ijk form. So we have our x component, so that's 17.7 I hat. Our y component is minus 30.6 j hat, and our z component is minus 35.4 k hat. Okay, so there's F1. Now we need to do F2. So remember, for F2, we're given these angles. These are our cosine direction angles. And again, you'll be given these equations in your equation sheet, so the only thing you need to know is how to apply them. But our equations are for our coordinate direction angles that the x component, and sorry, this is f2x, is going to be equal to f times the cosine of alpha. F2y is equal to f times the cosine of beta, and f2z is equal to f times the cosine of gamma. And these angles, alpha, beta, gamma, are the angles that our force is making with the x, y, and z axis. So let's start with the x-axis. First of all, we know F, the magnitude, is 100 pounds. That's given in the figure. And then we need to multiply that by the cosine of alpha, which is the angle that the force makes with the x-axis. So that's this angle from the positive x-axis to our force, F2, and we know that that is 120 degrees. Okay, for F2, again, it's 100 pounds times the cosine of angle beta, which is the angle that it makes with the positive y-axis. So that's given here is 45 degrees. And lastly, we have our 100-pound force multiplied by the cosine of gamma, the angle that it makes with the positive z-axis, so that's the 60 degrees. Okay, so let's plug those numbers into the calculator. 100 times cosine of 120 is negative 50 pounds. Okay, and then 100 times cosine of 45 gives me 70.7 pounds. And 100 times the cosine of 60 gives me 50 pounds. Okay, so let's gut check that. In the x direction, we're going negative. Yes, that makes sense. It's a little hard to see the way that it's drawn here, but we've got an angle with the x-axis. It's greater than 90 degrees, so we must be going back along the x-axis here. For the y component, we've got a positive number. Yes, that makes sense. And for z component, yes, again, that makes sense. We're going positive. Okay, so let's write it as ijk vector. F2 is equal to negative 50 I hat plus 70.7 j hat plus 50 k hat. All right, so we've just got one more vector left, and let me make some of this smaller to make some room. Okay, and we'll do it over here. So for F3, we know that it is 20 pounds, and we're given directions along each of the axes, but they're given to us in distances. So the easiest way, I think, to handle this is to first treat this as like a displacement vector. So we're making a displacement vector from O, our origin, up to the tip of F3. And that displacement vector, let's call it vector OA. And to make our displacement vector, we need to take the point A and subtract point O, which is all zeros. So what we're going to end up with is just our distances or our coordinate points for point A. So if I write that, we've got a distance of 4 feet along the x-axis, 4 feet, and that's in the positive I hat, and then also a distance of 4 feet along the y-axis, so j hat, and lastly we're going up along the z-axis 1 foot. Okay, so let me rewrite that as just 4i hat plus 4j hat plus k hat, and that's in feet. Now we need to turn this displacement vector into a unit vector, and that unit vector will tell us just the direction of F3, and we'll get rid of the magnitude of this displacement, which we don't really care about in this example. So to make a unit vector, first we need to know the magnitude of OA so we can divide it out, and that magnitude is going to be the square root of 4 squared plus 4 squared plus 1 squared, right? So I'm just squaring each of the components and taking the square root of the sum of those. I get 5.74 feet. So if we cared about this, we're not asked in this question, but what this tells us is that the distance from point O to point A, which is at the tip of the F3 vector, that distance is 5.74 feet. But what we need now is this unit vector OA, which is going to be equal to our original vector OA divided by the magnitude that we just found. So I'm going to divide each of my components. 4 divided by 5.74 is 0.697 I hat plus 0.697 j hat, and then 1 divided by 5.74 is 0.174 k hat. Okay, so that's a little messy. Let me move this out. So that I can write it all in one line here. Okay, there we go. Now we have the direction, OA, without the magnitude, and you can confirm that, right, by taking the magnitude of this vector. If you do the square root of the sum of the squares of each of these 3 components, it should come out to 1. Okay, and now we want F3, which F3 is going to be equal to the magnitude of F3, which we're given is 20 pounds, times the direction of F3, which it's pointing along this OA unit vector direction. So that's going to be 20 pounds times my unit vector, 0.697 I hat, 0.697 j hat, 0.174 k hat. All right, so let me multiply all of those through. 20 times 0.697 gives me 13.94 I hat. It's going to be the same thing for j hat, right? We're still multiplying. 20 pounds times 0.697 And now 20 times 0.174 gives me 3.48 k hat. Okay, so we've written each of our vectors in a ijk form, and each one of them started in a different way. These are the three different ways that you might see vectors given to you, if not already given to you in the ijk form. So if you can follow each one of these force vectors and how we transformed it into Cartesian coordinates, then you know all the tricks. So now the last part here, we've gotten a little sidetracked. Our actual ask is to find the resultant of the vectors f1, f2, f3. So let's do that now. The resultant is going to be equal to, resultant just means sum. So we're going to sum f1, f2, f3. And now that I've written them in this ijk form, this is going to be really easy. So I've got 17.7 I hat minus 30.6 j hat minus 35.4 k hat. That's f1. And I want to add f2. So f2 is negative 50 I hat plus 70.7 j hat plus 50 k hat. And f3 is 13.94 I hat plus 13.94 j hat plus 3.48 k hat. Okay, I'm adding all of these together. So I can just add all the I components, add all the j components, and add all the k components. So I'm just going to go vertically and add each column. 17.7 minus 50 plus 13.94 gives me negative 18.4 I hat, and then negative 30.6 plus 70.7 plus 13.94 gives me 54.0 j hat. And then lastly, negative 35.4 plus 50 plus 3.48 gives me 18.1 k hat. So that's my resultant vector. So see how once we get everything into Cartesian form, the rest is cake. Easy, easy. So now the last part of this question asks us to find the directional cosines of the resultant. And so we're going to use these exact same equations that we used for f2, except for now we're solving for the angles alpha, beta, gamma. So let's rewrite those equations just a little bit reorganized. We're going to say that cosine of alpha is equal to just fx over f. Cosine beta is fy over f. And cosine gamma is fz over f. So all this means is that we take the x component of our vector, divide it by the magnitude, and that's going to be equal to cosine alpha. The y component divided by magnitude is cosine beta, and z component divided by magnitude is cosine gamma. So for each one of these equations, we're going to need the magnitude. So let's find out the magnitude of our resultant vector. That is the square root of 18.4 squared. And really there should be a negative in there, right? But it's going to go away once I square it. So then we add 54 squared and add 18.1 squared. Okay, let's put that in the calculator. 18.4 squared plus 54 squared plus 18.1 squared. And the square root of that, I got 59.85. So that's the magnitude of our resultant vector. And let's pause for a minute just to think about that. We've got about 60 pounds, and that's the resultant of these three vectors that were 100 pounds, 20 pounds, and 50 pounds. So we're not just directly adding these magnitudes together, right? Or subtracting them or anything like that. You would not end up with this same answer if you tried to do that. Okay, so you've got to go through all these vector operations to get to the right answer here. Okay, and I guess another thing we could take a look at is our resultant vector, the direction that it's pointing, right? It's pointing in the negative x, positive y, and positive z. So let's look at that. We're pointing negative x, positive y, positive z. So we're pointing pretty close to the same direction as F2. And that seems to make a lot of sense to me because F2 is our biggest force vector here. So it makes sense that that would be the one that dominates. All right. So now we've done all that. Let's wrap this up by solving for our directional cosine angles. So fx, that's our x component of the resultant vector, which is negative 18.4, divided by the magnitude. We just solved for 59.85. And then for cosine beta, we take our y component, which is 54, and then divide by the magnitude, 59.85. And for the z component, we take for cosine gamma, we take our z component, divide by the magnitude, 59.85. So this comes out to negative 18.4 divided by 59.85. This gives me negative 0.31. And then 54 divided by 59.85 gives me 0.90. And 18.1 divided by 59.85 gives me 0.30. Okay, so let's do inverse cosine of each one of these to get the final answer. So for alpha, let me move this out of the way. So alpha is equal to the inverse cosine of negative 0.31. So I got 108 degrees. Beta is equal to the inverse cosine of 0.9. So 25.8 degrees. And gamma is the inverse cosine of 0.3. So that's 72.5 degrees. All right, there's our answer. And again, we can go up and try to make sense of this answer. Let me try to draw our resultant vector. So it's pointing 108 degrees from x, 25.8 degrees from the y-axis, and 72 degrees from the z-axis. So we've got something, it's 108 degrees from x, so it's a little bit shallower than the alpha angle for F2. Let me remember what this is. 25 from y and 72 from z. Okay, so pointing something like this. right? So this is our resultant vector. And these angles, we've got an angle here. This is our alpha angle. Here's beta. And then here, gamma. All right, so that is how you solve this problem. I think that's a good review of the operations we can perform on vectors. Well, there is one last thing, right? We talked about dot products. So the great thing that dot products are useful for is for finding the angles between any two vectors. So if I were to ask you, what is the angle between F2 and F3, we could solve that using an equation that, again, is in your equation sheet. It's cosine theta is equal to A dot B divided by the magnitude of A times the magnitude of B. So here, vectors A and B are F2, F3 force vectors, and we've already got them in Cartesian coordinates, so let's just plug them right in. Cosine theta is equal to, now we need F2, which is this one here. We just need that part. And then dot to F3, which is here. Okay, and divided by the magnitudes. Now, you can solve for the magnitude again by doing the sum of the squares of these components, square rooted. But we already have the magnitudes. That's what was given to us at the beginning of the problem, right? So if I look up here, the magnitude of F2 is 100 and the magnitude of F3 is 20. So 100 pounds times 20 pounds. And the units of these two vectors are also pounds. So pounds times pounds divided by pounds times pounds, it's going to all cancel out, and we will be left with something that is unitless. And that makes sense for a ratio that we're going to perform an inverse cosine on to get an angle out of, right? So this equation is dimensionally consistent. Now let's do our dot product. So remember, dot product, we're going to multiply each of the x components together and then add each of the y components and then add each of the j components. So let's write that here. So we've got negative 50 times 13.94 is negative 697, and then plus 70.7 times 13.94 is 985.6. And then lastly, we need to add 50 times 3.48. It's 174. Okay, and divided by 100 times 20, that's 2,000. Okay, so cosine theta equals negative 697 plus 985.6 plus 174 divided by 2,000. That's 0.23. And then when I take the inverse cosine, I get that theta is equal to 76.6 degrees. Okay, so that's our angle between F2 and F3. So that's our angle, do another color, here, between our two vectors F2 and F3. All right, so in the next video, we will get started with the next module and with chapter 3, equilibrium of particles.